My name's David Burgess, and I'm going to be talking to you, trying to convey some of the concepts and ideas to do with shocks and energetic particles. The overall scope was given to me as sun, wind, presumably solar wind, planets, and heliosphere, so that's about as broad as you can get. And really, I'm only going to mention certain areas. Other areas I'll try and go into a little bit more detail. Let's see if this works. So, oh, do you see it? Okay, but it doesn't come up here. That's good. Okay, everybody has got their poll. It should be, is it ticking down? I've given you 40 seconds. And you have to write something. You write the answer to the question. Why can't I see it up here? Can I see it up here? Share. I want to share my poll. Okay, are your 40 seconds up yet? So we can't share this. Okay, we can do that now. Oh, great. Brilliant. Look, we can't share this?
No.
Okay, well, I'll read it out. It's okay. Okay, fine. I just wanted to see if it worked okay. It kind of worked. I got 6 people answering my question. So what is a shock? Discontinuity. Okay, 4 marks, Karina. A collision between a supersonic and subsonic fluid flow. When a wave travels faster than the speed of the medium. That sounds quite deep. Some kind of discontinuity. A pileup of the plasma. A discontinuity in quotes in velocity and density. All of those things are pretty good. Unfortunately, I can't share those with you. I mean, I can't put them up, but let's carry on. Okay, so that's actually already good. So I know 6 of you actually probably already know the basics. So the people who didn't answer in time were either shy or you don't know the basics. But we're going to put all of that all together. So I'm going to talk about why we have shocks, why we have them in the system. I'm going to give you lots of sort of just examples of shocks in the solar system, in the heliosphere, I should say. And then I'm going to try and just introduce you to some of the ideas of shock physics. And they're sort of the things I'm going to talk about are up there. And then the second lecture, we'll be talking about the connection between shocks and energetic particles, because as we've already heard in the morning's lecture, if we're looking at things like space weather, if we're looking at things like trying to send astronauts to interesting places, energetic particle environment is really important. And the sun, we know, is an active star, flares and so on. We know those are all characterized by energetic particles. So flares aren't the only source of energetic particles, so there are lots of other sources, shocks being one of the places where you can accelerate particles. And so it becomes an interesting question in terms of a universal process, because shock waves are something that will happen in any plasma, with the right kinds of flows. Okay, so we had the idea that a shock is a collision between a subsonic and a supersonic flow. I don't really like the word collision. Let's say transition. It's a transition between a subsonic and a supersonic flow. So there's a link between supersonic and shocks. We kind of already know that, don't we? Because supersonic aircraft create shock waves, and they go boom and rattle windows. But let's think about why we need to have something which is supersonic. So supersonic means faster than the speed of sound. So in this room where it's full of neutral gas, there's a characteristic speed. It's the sound speed. Sound speed is related to the pressure gradient. So when you do the standard little derivation about sound speed, you think about pressure variation. So a sound wave is a pressure wave. So if I take my hand and I just move it through the air here, it's not moving very fast. It's moving less than 300 meters per second, I think. So it's subsonic. So the gas has to move out of the way of my hand, obviously. It displaces the air as it moves out of the way. So what is the force which moves the air out of the way? Pressure. It's the only force there. Correct. So it's the pressure force. The pressure wave moves at the sound speed. So what's going to happen when I try and move my hand through the air at supersonic speed? Clearly something that is not going to quite work, is it? Because I'm trying to move something through this medium. The force which is telling the gas to move out of the way is pressure force, and that information only travels at the sound speed. But this thing, my hand, is trying to move faster than the sound speed. So we find that there is this important distinction when we have an obstacle which has a supersonic speed, a supersonic relative speed. Don't mean relative speed. I could be holding my hand stationary, and the air in this room could be moving supersonically, being sucked by a great big fan at the back of the room. Okay, so it's relative speeds. Always think about relative speeds here. So we have this idea that if we have a supersonic obstacle, we need to have this extra ingredient, the shock wave. Now, when we think about moving supersonically, I still have got to displace gas around the obstacle. And the only force left to displace the gas is pressure, still. So we're actually, if you follow that logic through, we're saying even if this obstacle is moving supersonically, we still need to have a subsonic layer next to the obstacle in order to push the gas around it. Okay? We still need that supersonic layer. Subsonic. It's like saying left instead of right. Subsonic layer around it. But we know that the relative speed between the obstacle and gas far away from the obstacle is supersonic. So somewhere in between, there is going to be a transition from a supersonic relative speed to a subsonic relative speed. And so that's what the shock is. The shock is that transition between supersonic and subsonic flow. That's one way of looking at it. Why it's got to be a discontinuity is an interesting question, but you could, and we're going to talk about that a little bit later. But the fact is that we end up with a wave which is, discontinuous or close to being discontinuous. Okay, so we can look a little bit at this idea of the necessity of having a transition from subsonic to supersonic flow by thinking about the disturbance created by a single point. That disturbance spreads out at the speed of sound. And you then say, well, now my little thing which is creating the disturbance is moving at a certain speed. And if the speed that it's moving is less than the speed of sound, which is in the picture on the left, then essentially that disturbance will spread out through all of space. And it's basically going to be spreading out around that point. So the point that's creating the disturbance will always be inside the region which has been communicated to. But if, on the other hand, the thing that is creating the disturbance is moving sufficiently fast, then actually it creates a disturbance, and then that disturbance expands at the sound speed, but the thing creating the disturbance is moving faster than the sound speed. So it will basically leave behind the disturbance behind it. So it creates the disturbance goes out at the sound speed, and in the time that it's got to a certain distance, in that time, the disturber, the obstacle, has actually moved beyond that sphere of influence. And what happens when you then think about putting together a whole sequence of these little disturbances you end up with something that's called the Mach cone. And so what we're doing is we're saying we've got a disturbance which is moving along. I want to use the laser pointer, but on the other hand, I don't want to use the laser pointer because I know that sitting at the back, whenever anybody used the laser pointer, I couldn't see it. Has anybody ever seen the laser pointer on the screen? Right. Okay. I'm not even going to use that. Oh, I could use. You're right. I could try and use this pointer. Let's see if. Okay, now it's disappeared. Oh. Oh, okay. Oh, okay. Right. Fine. Okay. So what I've got is this region around here, which is where the obstacle is, and so where the obstacle just is, it's just created a disturbance, and the disturbance hasn't moved very far. But if I go back in time, then the disturbance that was created longer ago has expanded a larger distance. Within this envelope of these different disturbances, within that envelope is the region that can be communicated with subsonic flow, or flow with information at the speed of sound. So behind here, this is all flow that can be influenced in a subsonic fashion. On the other hand, outside of this envelope, that region can never be communicated to by the obstacle. In other words, that's the supersonic region of flow. It's like, you shout into the wind and your sound wave gets swept behind you. So this Mach cone, in this case, is the discontinuity between a flow which is supersonic and flow which is subsonic. As you can see, this is for a point disturber, and we have a cone. You can actually see what that cone looks like by these Schlieren-type photographs of shock waves in wind tunnels, and you're familiar with these pictures, and then the transition here is the shock wave, and in this case, of course, you can see secondary shock waves. Also, if you have a blunt obstacle, things are slightly more complicated because you have to consider the pile-up of the material as it comes across the obstacle and then is carried around the sides of the obstacle, and that leads to a shock wave which actually stands off in front of the obstacle. And then this is beginning to look, this right-hand picture here is beginning to look very much like the cartoon of the magnetosphere, where we have this, we've already seen the cartoon of the bow shock standing off in front of the obstacle, which is the magnetosphere. So the fact that the bow shock stands in front of the magnetosphere is because the magnetosphere is a blunt obstacle. If it was more pointy, then the standoff distance is not as large. And if it was larger and flatter obstacle, the standoff distance would be greater. Okay, so that's shocks in a neutral gas. But shocks in plasmas, we follow a very similar sort of story. We have the same idea of a transition between supersonic and subsonic, but now sonic, which meant sound speed. Well, that doesn't really mean, we don't really mean sound speed anymore, because we know that in a plasma, at least if we want to use MHD, then there are a variety of wave modes, and we have to think about fast mode, slow mode, intermediate perhaps, and other things like that. So we have to think about the wave speeds, the characteristic wave speeds in a plasma if we're going to talk about super and sub-sonic. On the other hand, in our system with the solar wind speed, high solar wind flow, the alphane speed is only 50 kilometers per second. The fast mode speed is roughly speaking, of the same order. And we know that there are also impulsive events in our system, like flares, CMEs. We know that we have obstacles like comets, planets, whether they're planets with magnetic fields or planets without magnetic fields. So we know really that there have to be shocks. There's a nice little bit of history about shocks in plasma physics, because as with many things, and especially the space physics, it really took off with Sputnik and 1960s and space technology. Shocks were originally, or most studied for the effect in warfare for blast waves of explosives. The importance of shocks in plasma physics was actually to do with basically nuclear weapons. And so a lot of the original work on shocks in MHD plasmas was classified work. This was work from the 40s up until the mid-1950s or so. And the picture on the right, by the way, is a picture of Starfish Prime, which was one of the last high-altitude atmospheric tests carried out by the States. So that's what that's in 1963. Is that right? Thank you. I've got a memory for dates. No, I haven't. I'm just lying. The little abstract there is one of the first and kind of really one of the important papers that actually still gets cited nowadays about MHD shocks by somebody called de Hoffman and of course Edward Teller, the father of the atom bomb. And there are some shock physicists relaxing. With their husbands. So we have this history so there's an interesting little bit of history about it. So that's why when you look back in the literature and why everything seemed to start suddenly in around 1950, 1955. It was actually tied to the declassification of a lot of the nuclear work. So I'm just going to run very quickly through some of the places that you're going to find shocks in the solar system. Almost everywhere you look, you'll find a shock when you have a flow and, as I said, a sufficiently large difference between something that can be an obstacle and something that can be a flow. Now, it doesn't have to be an obstacle as such. Sometimes you can have just a difference in flow speeds. So when we look at interplanetary shocks, these are shocks caused by sudden changes in the solar wind speed. So if you have a region of slow solar wind and then behind it a region of fast solar wind, the fast solar wind plows into the slow solar wind, and that interaction causes shock waves. So we've got CMEs, which are these impulsive events. We have essentially, what have we got here? Yeah, so CMEs, two examples here. This little diagram just points out the fact that the shock wave is a wave that is launched in front of the obstacle. So as we see in this picture here, the shock around here is actually in the solar wind in front of the change in flow which is creating it. So when we talk about a CME and we talk about the shock that precedes the CME, so very often we always think, well, the CME has a shock. There is a slight distinction between the structure which is creating the shock and the medium, the plasma, into which the shock wave is propagating. This is yet another picture of a CME. Once we get further out, it's sometimes called an ICME, interplanetary coronal mass ejection. And then we've put on some field lines in here, and we're going to introduce this several times, but I just introduced the fact that we can actually label different regions of this shock depending on the magnetic geometry. And by that I mean the orientation of the shock surface relative to the magnetic field line. So for example, in this side where we have something that we would call a quasi-parallel shock, the magnetic field lines are approximately parallel to the shock normal direction. And conversely on here, where we call it quasi-perpendicular, the shock normal is perpendicular to the field lines. So We're going to return and see what that means in a second. As I said, as I just mentioned, that we can also get shock waves when you have a difference in flow speeds. And there, because if you think of the sun and it has regions of fast solar wind, regions of slow solar wind, and sometimes the coronal hole is a region of slow solar wind. So if you're at the ecliptic plane and you have a coronal hole which comes down to the equator, that will be a source of fast solar wind. And then as the sun rotates, you will essentially have slow solar wind, and then behind it fast solar wind, and somewhere else around, as the sun rotates, you'll have fast solar wind and slow solar wind behind it. So you have these compressions and rarefactions. And the whole pattern will actually also rotate with the sun. Essentially, it's the pattern on the solar surface which is rotating. And that's carried out into the heliosphere. And so we get these things which are co-rotating interaction regions. And the co-rotating interaction regions are bounded by shock waves. And that little picture is sort of demonstrated here, how you start with, for example, if you had the solar wind here, where you have essentially slow followed by fast. In the density, what you'd find is the change in density, and you find these shock waves. That's going to be seen a little bit clearer when we just show you this picture, which shows that the general morphology of these co-rotating interaction regions, where you have an interface between the different streams, that's the fast stream and the slow stream, and that's stream interface. And then launched ahead of that interface, you have you have what's called the forward shock, and then behind it you have a reverse shock. So if you remember, it's all about relative speed. So we've got here a blob of solar wind which is traveling outwards. But as it travels outwards, one bit is going faster than the other bit. So there's a relative speed between those two parts. And then within that relative speed, that's what launches some shocks. And so the shocks go forward and backwards, but in that frame which is moving with the stream interface. So both shocks are actually moving outwards in the sun frame, but we can label one as moving forward in the solar wind frame. That's the forward shock, and another one which is moving backwards in the solar wind frame, and that's the reverse shock. That can sometimes be confusing. So when we see what one of these co-rotating interaction regions looks like in time series data, we can now see profile in time, and we can see the profile of the forward shock here in velocity. And so we have a velocity which starts off at 400 and jumps up to 550. And if you notice, that jump is very abrupt. Okay, so that's, it's a shock. Something that happens abruptly over a short distance, we call a shock. And so when people say a shock is a discontinuity, that's what we're talking about here. We're looking for discontinuities in the flow. So we have a forward shock here where the velocity changes, and also the magnetic field changes sharply here. The magnetic field change is also a little bit, you have to be careful that there's a change due to the shock, which is right down here, and then there's a change due to the overall structure of the compression of the co-rotating interaction region. Okay, but the shocks are actually, as I said, they're in the plasma outside of the central material, and they're actually propagating into, clean solar wind. And then on the other side, we see the reverse shock. The point about here is that we've also got energetic particles, and that associated with this forward shock especially, you can see a large spike in the energetic particles. So there's a link between the interplanetary shocks and energetic particles, and that's what the second lecture is going to be talking more about. Okay, how many times have you seen this picture? Okay, how many times have you seen this picture? Okay, so I'm going to talk about the Earth's bow shock, mainly because that's what I know about, and it's usually better to talk about what you know about. And so the Earth's bow shock, as I said, it's a shock which stands in front of the magnetosphere, so the magnetopause is the obstacle. The magnetosheath is the region of solar wind flow, which is now subsonic. So between the bow shock and the magnetopause, we have the magnetosheath. So from a shock physicist's point of view, the magnetosheath is the flow which has been decelerated from supersonic to subsonic. And because the magnetopause is a blunt obstacle, we have a curved bow shock. And so what we're looking at here is just basically a two-dimensional cut through the structure. So this is the bow shock shape. And again, we have, I'm just highlighting the importance of the magnetic geometry in the sense that I've labeled here two sort of regions. One region, quasi-parallel shock, one region, perpendicular or sometimes quasi-perpendicular shock. So here, on this side of the shock, just because it's a curved shock, on this side, on one side, we have the field lines being perpendicular to the shock normal, and on the other side, on this side, we have the field lines which are approximately parallel to the shock normal. And you'll see in this little cartoon that on this side, in the quasi-parallel section, the artist has suddenly got a little bit of the shakes and drawn a lot of cartoon turbulence. And on this side, there isn't that cartoon turbulence. And so that's telling us that the quasi-parallel shock is associated with a different kind of structure, a different kind of environment compared to the perpendicular, quasi-perpendicular. We're going to return to that, the difference between these two types of shock. Also in the cartoon, we've got some information about energetic particles. Now, the shock is going to, I'm going to show you, I'm going to demonstrate how the shock can accelerate particles. But we can just say that from observations, we put lots of spacecraft through here, from observations, we know that the shock can produce energetic particles, energetic electrons and energetic ions. Not only that, but the types of ions can be different types in terms of their velocity distributions. So we can sometimes see aligned, what are called field-aligned beams. This is a little picture of a distribution function. The main peak here, the tall peak, is the solar wind, and there is a secondary peak which is only slightly broader than the solar wind, and that's a beam of accelerated particles. So this is a collimated beam. Whereas around here, slightly different spatial location, again, the main peak is the solar wind, and you see that there is a near isotropic increase of energetic particles as well. That's called the diffuse ion population. And as I said, these extend to higher energies. They have a different velocity distribution. Okay, we also have something called the electron foreshock. So everything in front of the shock we call a foreshock. So if it's got energetic particles there in front of the shock, we call it a foreshock. And the electron foreshock is where we find the energetic electrons, and the most energetic electrons we find almost on the field line, or very close to the field line, which is tangent to the shock surface. So we've got this curved shock. If you imagine an upside-down bowl, curved shock, and then you put some straight field lines on there, there'll be something called a tangent surface. There'll be a surface made up of the field lines which are tangent to the overall shock itself. And we find the most energetic electrons on that tangent surface. That kind of makes sense because if you remember, of course, we've got a solar wind flow here. So that solar wind flow has just got a convection. Any particle that you put in this system is going to have a solar wind convectional flow imposed on it as well. So even if we accelerate a beam parallel to the magnetic field, it's going to have on top of it the solar wind convection. And how far a particle moves downstream because of that convection depends on how fast it's moving. This is the problem of the swimmer crossing the river. The faster you can swim, the more straight across the river you get. So the faster the particle is going, the closer it stays to the field line in this sort of picture. Now, electrons have low mass. So if you give them some energy, they are very fast. And so the fastest particles, which in this case are the electrons, they move away from the shock closer to the field lines in this cartoon, okay, in this frame, which is the shock frame. Okay. Okay. So what we want to do, okay. No, didn't know this one was coming up. Okay, so I just wanted to say, of course, that the bow shock, we've got fantastic observations of the bow shock. So when we put a spacecraft around the Earth, it has a when it gets out to the bow shock region, it has a velocity. The spacecraft velocity in the Earth frame is a few kilometers per second. The shock itself is not completely stationary. It is always reacting to changes in the solar wind speed and solar wind density and so on. And so the shock itself is always moving inwards and outwards slightly. Now that velocity is of the order of 10 to 50 kilometers per second. So actually we can think of the spacecraft as stationary, and we see the shock at the spacecraft because the shock moves. Maybe it moves inwards, maybe it moves outwards. Okay? And so when we take time series, we can get profiles of the magnetic field which look like this. Here is the top frame is a system where the field is low and then becomes high. If I plotted the velocity, it would have been high and then low. So this is actually what we call an inward crossing of the shock. In other words, we're going from solar wind through the shock into the magnetosheath. On the other hand, this event down here, we are in the magnetosheath with high magnetic field, and we pass into the region of low magnetic field, which is the solar wind. So we're going outwards from magnetosheath to solar wind. You can just see from these different crossings that not all shocks look the same. They look different from each other. We're going to find that these are mostly quasi-perpendicular shocks. We will see that there is actually a unifying structure to them. But you can see that there are different features. We can sometimes see an increase in the magnetic field right close to where the main shock is. We can certainly see that downstream of the shock, we can find lots of waves and turbulence and so forth. So all of these things are, the different kinds of appearance of those shock crossings are all lumped together and called shock structure. So why is that important? It's important because, one of the definitions right at the beginning was a shock is a discontinuity. And actually creating a discontinuity in a collision-less plasma, when you think about it, is pretty difficult. If you completely believed in no collisions and you just put something hot next to something cold or something fast next to something slow, and you created a discontinuity, then you think if I didn't have any collisions, it would soon wash out. Yeah? The fast and the slow would interpenetrate, and I wouldn't have a discontinuity anymore. So one of the big problems, one of the things why collisionless shock physics is interesting, is working out how, in a collisionless plasma, you can continue to have solutions which look as though they are almost a discontinuity. Okay? In other words, they happen over a short time and length scale. But they're not perfect discontinuities, and they can't be perfect discontinuities because they need to have some structure. They need to have some way of coupling the upstream and the downstream flow in the right kind of way. And that relies on the interaction between fields and particles. And we'll get onto that in a second. So we've spoken about shocks on the sun created by CMEs, interplanetary shocks, shocks because of stream-stream interactions, the Earth's bow shock, which is an example of planetary obstacle. Of course, we have bow shocks at other planets as well. And finally, just so I can mention it, the heliospheric termination shock. In fact, Joe Giacoloni spoke about this already, so I'm not going to spend very much time on it. But just to say that even if you go out to the edge of the heliosphere, and the heliosphere is very big, nevertheless, you could find a shock which has got a very sharp transition, basically nearly a discontinuity. And here, the top frame here, you can see a change, very rapid change in the velocity corresponding to that the termination shock. So this is the shock. And you kind of say, well, where's the obstacle? I think Joe already described this well. The obstacle is actually on the outside. The obstacle is all around us. It's the local interstellar medium, and the supersonic flow is on the inside going outwards. And so we have this shock, which is an interior shock. In fact, you can think of it a little bit as a reverse shock. It's a little bit like a stream-stream interaction, very similar to a co-rotating interaction region. And the termination shock is the reverse shock. Okay. It depends how you want to define Mach number. It depends which pressures you count in, because if there's the pickup ions are an important pressure here. But if you just took the standard solar wind part of the flow, then its Mach number is high-ish. Joe will tell you exactly. 5, 6, 10. Joe's not here, so I can guess. Yeah, yes, it's still relatively speaking high, but it's a complicated shock. Joe spoke a lot about the anomalous cosmic rays, about the pickup processes. As you go out in the heliosphere, these other energetic particle populations become very important in terms of the overall pressure budget, and therefore these shocks can become what we call, they're complicated shocks. How many more minutes do I have? That was a 5. Okay, you know how many more slides I've got to get through. Okay, so as I said, that the collisionless shocks are really interesting because we're trying to work out how we can have a discontinuity despite having no collisions to do our dissipation. So we've got to do our dissipation through coupling between the electromagnetic fields and the particles. By the way, shocks aren't a problem in a neutral gas with collisions. So in this kind of gas, it's the collisions which provide the limit for the width of the shock. So it's basically a shock in a normal neutral gas, that the width is the collisional mean free path. Okay, but the problem with a collisionless plasma, we don't have any collisions, so we don't have a collisional mean free path, and we have to use other things. Now, but we can actually, it's really clever. We can put all of that interesting collisionless plasma physics to one side, and we can actually still learn a lot about shocks simply by using conservation relations. In other words, we simply say, let's take, energy, mass, momentum, these are all going to be conserved. We've got a shock which is propagating through a medium, so we've got material which is on the upstream side, which passes through the shock and then passes downstream. And so we can take a system around a shock and say, let's just conserve energy, let's just conserve momentum, let's just conserve mass. And then it doesn't matter what the shock looks like. Okay, we're simply saying that there is an upstream and a downstream. And we can, it turns out, we can actually come up with a closed set of equations which relate the downstream parameters, that's how fast it's going, how hot it is, etc., to the upstream conditions. Again, how fast the flow is, how hot the flow is, which essentially is the properties of the shock itself, which is the shock strength and so on. Okay, so we want to do this in MHD. In neutral gases, this is called the Rankine-Hugoniot relations. It dates back to the 1880s or something. But in MHD, it's complicated because we've got several wave modes. We've got the sound speed, we've got the alphane speed, so we've got different characteristic speeds as well. As I said, what we're going to do is we're just going to say there's an upstream and a downstream, and then there's a region in the middle that we're going to call a shock, and I don't really mind what it does as long as it conserves mass, momentum, and energy. And so I simply label the upstream quantities with subscript U, the downstream quantities with subscript D, and I have the shock normal is N, so if you see a subscript N, that means the normal component. If you see a subscript T, it means the tangential component, in other words, tangential, which is in the plane of the shock surface. Now, if we take any quantity which we can write a conservation equation for, we can write it in this first way here. So we write it like this. This is a conservation equation. We have a quantity Q, which has an associated flux M. So we can have mass and mass flux. And we can, if we assume one-dimensional, if we assume time stationary, so the dq dt term can just go away, the divergence term is now just a one-dimensional ddx, this equation we can just integrate from upstream to downstream. And then we end up with a relationship which I've written it in a rather strange way. These square brackets, this is just a shock physics convention. Square bracket means that we're just looking for the difference in the quantity across the shock. So it's the upstream value minus the downstream value. And we just use these square brackets. It's just a shorthand notation, so we don't have to keep saying upstream minus downstream. We just say it's the quantity, put square brackets around it. That means that's the difference in that quantity from upstream to downstream. And so this is the general thing we're going to do. We're going to do it for mass, momentum, energy, and so on. So let's just take the conservation of mass. That's the conservation of mass equation, nice and simple. And then we just look and say, well, this is my rule. If I've got an equation that looks like this, I can write down a conservation equation that looks like this. So here we go. The difference, the change in rho Vx, oh, that should be n, so that's the normal velocity, okay? The normal mass flux doesn't change across the shock. So in other words, the mass that's going into the shock in the normal direction, that mass flux in equals mass flux out. Nice and simple. Mass is conserved. Mass flux in has to equal mass flux out. Right, now we can do the same thing for the other equations of MHD. Essentially what you do, you take MHD, you write it in conservation form. That's not always the way it's written, but if you rewrite MHD in conservation form, you can very quickly write down these shock conservation equations. The first one is conservation of the normal momentum. And you can see that we've got this term here, which is the pressure term. So that's if you think about the pressure, it's just a one-dimensional system. The only pressure force is going to be normal to the shock. Okay, so this is our normal force here, and you've got a B squared, so that's like magnetic pressure. Then we've got the transverse momentum, which is our equation here. We've also got an energy conservation equation for energy. You can see there's a half V squared here times rho Vx, so that's the kinetic energy flux. And we've got the associated thermal energy flux in here, and so on. So all of these first three are conservation of momentum, conservation of energy. Okay, where do you think the next one comes from? Yes, divergence of B. So now we have to go a little bit out. We have to start using Maxwell's equations. Div B equals 0. We put that into a one-dimensional system, and we get the change of the normal component, the Bx. This is the normal component of the magnetic field is 0. So the normal component is continuous. And this last one is the continuity of the transverse electric field. Okay, that also comes from Maxwell's equation. So we've got that the tangential electric field. This is the electric field which is parallel to the shock surface is continuous. Okay, now if you take those equations, have I got minus 2 minutes or plus 2 minutes? 30 seconds. So if we take those equations, you can solve them. And unfortunately, it turns out that things are more complicated than we want them to be. Because we've just started from MHD. We haven't, at this stage so far, said, I only want shocks. Okay? And it turns out MHD gives us lots of other things. It gives us, in fact, all of the possible discontinuities within MHD. Okay, so what's the difference between a discontinuity and a shock? Well, a shock is a discontinuity, but a shock is a discontinuity which has a normal mass flux and at which the entropy increases. So we actually got to add some extra bits of physics here, because we want to have a change from upstream to downstream which is irreversible. Okay? And so it turns out that we want the entropy to increase. So some solutions within MHD which look mathematically valid, we throw away if the entropy isn't increased at the shock. Also, shocks, by definition, have got a compression across them, so they have to have a mass flux, and this all holds together. So, but there are some other discontinuities where you don't have any mass flux. These are the tangential discontinuity and the contact discontinuity, which is basically just the field doesn't change, but you just get a pressure balance. You also have rotational discontinuities, which propagate at an alphane speed, but that doesn't work as a shock. Okay, so the rotational discontinuity doesn't get classified as a shock. So we have this whole hierarchy of different discontinuities, but as I said, we're just going to concentrate on the discontinuities where we've got shocks. So we have a compression in the density. We have an increase of entropy. And we're also then going to be able to classify different kinds of shocks, whether they're oblique, parallel, perpendicular, depending on the essentially the normal component of the magnetic field and this magnetic geometry. Okay, so I just wanted to show this, that there is this, the conservation equations give you all the discontinuities that people will start talking about those already in this week. So they're buried in these conservation equations as well, and sometimes you don't talk about them, but they're there. Okay, so let me just finish this little section by saying what I mean. As I said, in MHD we have got these different wave speeds, so how does that translate? Because right at the beginning we said the sound wave, supersonic, subsonic. So what happens when we have several wave speeds? We've got the fast wave speed, slow wave, and the intermediate, or the alphane, shear alphane. It turns out, when you kind of do things properly, that there are in fact only two kinds of shocks which are valid as real shock waves. And that is the fast shock and the slow shock. The fast shock has the properties of a fast wave. That is to say, the density and pressure increase in phase with the magnetic field. So the density increases and the magnetic field increases together. Okay, so if you had a profile of the density and a profile of the magnetic field, they look the same. That means, of course, if the field increases from upstream to downstream, here's upstream, here's downstream, so there's a field increase, that means the field lines have to get closer together, and so you actually get a kink in the field lines like this, they turn away from the shock normal. On the other, on the other hand, a slow shock, things go in the opposite direction. The density and the field are in antiphase, and so that means from upstream to downstream you've got a compression. So the density increases from upstream to downstream, but the field decreases. So in that case, the field lines have to get further apart, and so they actually bend towards the shock normal. The fast mode shock, wherever you have a fast flow, so the upstream flow has to be faster than the fast speed, and the downstream flow is slower than the fast speed, but faster than the alphane speed. Okay, but what does that mean? That means that if I just get an arbitrary flow, which is arbitrarily fast, then I'll find a fast shock. Okay? If I've got a slow shock, it's actually slightly more tricky because the upstream flow has to be greater than the sound speed. That makes sense because it's going to be the transition across the slow speed. But it also has to be less than the alphane speed. So by definition, slow shocks are low Mach number. They're weak shocks. Okay, you can't have an arbitrarily strong slow shock. I think that's the right expression. Those are kind of some subtleties, okay? It kind of says that if you want to take away from that, it says that most shocks that you're going to find are going to be fast mode shocks, and that's what we're going to concentrate on, and that's where I'm going to cut it. Okay, Question, well, 2 questions, and then I'll shut up. And sorry, you can have your break. Yes.
I know that the KDB virtual equation also gives shock-like solutions for shocks. And how do those shocks differ from these kind of shocks?
Sorry, which equations?
KDB virtual equation.
Yeah. Essentially that any hyperbolic system, okay, any hyperbolic system of equations will give you shock. So essentially that you can have many different kinds of equations which will give shock-like solutions. In other words, it's a discontinuous solution. So that's what you're interested in. So MHD is just one example of a system of equations that will give shock solutions.
Because even I think if I use MHD model, I can write KDB virtual equation and I can have shock-like structures.
And well, that's usually with some approximate. You usually, yeah, we could investigate that, but in principle, what I've said is correct. Okay, it doesn't matter what model you have, as long as that model has certain properties, then you'll have shocks. You have shocks in the equations describing traffic flow. Okay, if you ever thought about why you're driving on a freeway, and you suddenly stop, and then if you notice the transition of where the shock, where the cars stop, that transition moves relative to the flow. And it's caused by somebody having a puncture or, slowing down or having a drink of water or something. And so that shock propagates through the flow. So you get in lots of different systems, as long as you have a hyperbolic, essentially if you have something which has a speed of information, then you get a shock. Yes? But yeah, reverse shock. You mean?
We have the forward shaft and also reverse shaft. Whether in insulator we get reverse shaft also. So whether we can use any.
Yes. The important thing is the frame that you use. That you must transform into a shock frame and then use the Rankine-Heliophysics relations. Okay, right. Let's take a break. I'm sorry to go on so long, but you were enjoying yourselves. Okay, thank you. We'll take a break. We're back in 10 minutes.